Now we're going to model Newton's third law, that for every action there's an equal and opposite reaction. Or more precisely than that, if two bodies exert forces on each other, the forces are going to have the same magnitude, but opposite directions. And the way we're going to do that is we're going to model two objects connected by a spring. And so they're both feeling a force from the spring between them, and they're going to feel opposite directed forces. So I'm going to start by deleting some stuff here. Instead of having these arbitrary external forces, we're going to have the forces be based on a spring. So you see here, after I deleted Fy, I'm getting this error that there's nothing named Fy. And that's because we have this Fy here in the code that no longer exists anywhere. I'm just going to go ahead and delete, well, I'll comment it out for now. I'm going to comment this code out so that I don't get that error. I'm going to delete this other one. And the other thing I'm going to do, right at the beginning, I'm going to create two turtles instead, because we're going to connect them with a spring. And then I'm going to ask one of those, we'll just do the first one, turtle 0, to set its x-core to be x-core plus, let's say, 4. So now we're getting these two turtles. Right now it's drawing a line. I don't want it to draw that line, but I do actually want a connection between them to represent the spring. So I'm going to ask this turtle to create link with turtle 1. And that will create this link. And links are another type of agent in NetLogo that link together two turtles, and they're actually their own type of agent. So here I'm inspecting this link, and it has a color. I can make it blue. It has a thickness, so I could make it thicker if I want. And just like with turtles, right after creating one, you can do an open bracket and give it some commands. So I'm actually going to ask it to set thickness to be 0.3 so that it's easier to see. Okay, so now we've got our two masses here connected by this link to represent the spring. And we want these turtles to feel, these masses to feel a force based on that spring. So we're going to use Hooke's law, which says that the force of a spring is equal to some constant times the displacement. And it's the displacement away from an equilibrium length. So these are two parameters we need. So I'm going to make a slider here for k, and it can't be negative. Increment by 0.5, let it go up to 5. Okay, and then for the equilibrium length, let's go ahead and make that a global. Call that EQ length. And down here in my setup, I'm just going to set the equilibrium length to be equal to 4. So this length that we're starting with here. And okay, so we've got our two turtles here. We've got a spring. Now we want to accelerate based on the distance away from that equilibrium length. So r here is actually going to be equal to the equilibrium length minus the distance between the turtles. So if the equilibrium length is 4, if the distance between the turtles is greater than 4, then this whole thing will be negative. And we're going to define a negative force as pulling them together. And if the distance is equal to 4, there'll be no force, which is what we want. That's the equilibrium length. And if the distance is less than 4, meaning they're compressed together, then we'll have a positive force pushing them apart. So if we go over here, we're going to accelerate. When we accelerate, we're actually going to ask the turtles to accelerate the other turtle. And before I do anything, it's actually very important when doing this, now that we're doing Newton's third law, where each turtle, every action, there's an equal and opposite reaction, it's very important, I'm also going to get rid of this draw dot, that both the turtles calculate their acceleration before they move. Because if one of the turtles, when we ask the turtles, they go in sequence, in a random order, but they are calculating things in a sequence. So if one of them moves and then calculates its acceleration, and then the other one moves and then calculates its acceleration, they're going to be calculating their accelerations at different distances from each other, and they won't get the equal and opposite reaction. So we're going to separate these and have the turtles first accelerate. And then once they've both calculated their acceleration, then we'll ask them both, or later on we'll have more than two, ask them both to move. Very important to do this. Okay, so in our acceleration, each turtle is being asked to accelerate, and we're actually going to ask the other turtles. This might look a little funny, but we're doing it in a general way so that this will easily extend to more than two turtles. Each turtle is going to accelerate the other turtles. So we're going to ask the other turtles to, first of all, we want to get the force based on this formula here. So we're going to let the force be equal to EQ length minus distance myself. So each turtle is asking the other turtle, calculate the force based on the distance between you and myself and the equilibrium length. And then what we want to do is, right now we're going to just do this in one dimension, but we want to make sure we're getting the direction right, because for this turtle, let's say they're close together, so they're repelling each other. For this turtle, that'll be a force to the right, but for this turtle, that'll be a force to the left. So we have to take that into account somehow. So we're going to ask the turtle to face myself. So this turtle is asking the other turtle, face me, and then we'll actually turn around to face the other way so that we get the sign right. And then we're going to let the acceleration in the x direction be equal to the force divided by the mass times dx. dx is for each turtle, it tells you if it were to move forward 1, how much of that would be in the x direction, and it can be positive or negative. So if the turtle is facing to the right, then dx will be 1. If it's facing to the left, dx will be -1, but if it's facing up at a 45-degree angle, then dx would be just the x portion of that movement if it took a movement of 1. And so basically this is giving us the x component of this force because we faced the direction, the opposite direction of the other turtle, which is the direction that we're defining the force in from the spring. And then we're saying, just give me that x component. And then after that, we'll set our velocity, Vx, to be what it currently is, plus, as we've done before, ax times dt. We could have just put this directly in dt, but at this point, the acceleration formula has a few terms in it, so we're going to calculate the acceleration and then update velocity as the current velocity plus the acceleration times the time step. Just like with the x-coordinate, both coordinates for position, we update the position plus the velocity times the time step. Here it's the velocity plus the acceleration times the time step. Okay, so let's go ahead and see if that works. So I'm going to click setup, and these are starting at the equilibrium distance. So let's try moving them further than the equilibrium distance. And there we go. So they're exerting a force on each other, getting close, and then when they get too close, they exert the opposite force and they push away, and we see that they're moving symmetrically. Now they're moving symmetrically because they have the same mass. We could change the mass of one of these. Let's set this one's mass to 10, let's say. And, m. And now we'll see that this one is moving much more than this one because this one gets accelerated less given that it's a heavier mass. So we sort of get that for free based on how we coded this. I'm going to go back to having them the same though, for now, and we can always play around with that. This plot is now not very informative, so I'm going to change this. Instead of being Vx, let's make it Vy for now. Or sorry, Vy, instead of Vy, let's make it Vx. And now we can see the x velocity is changing in a sinusoidal way, as we would expect from this system. Okay, so we've got the basics working. Now we want to do it in 2 dimensions, which is quite easy. We've already set it up for ourselves to be quite easy, which is we just want to do the same thing in the y direction. So let ay be f divided by m times dy, and then set vy to be vy plus ay times dt. And so now we can do this in 2 dimensions. So instead of doing set x4 plus 5, let's just do forward 5. So now it's going to be in some random direction. And we'll see that it still works in that 2 dimensions, just as we expected. And actually I'm going to take these so that they're not a circle. And so we can see which way they're facing. At the beginning, they're facing random directions. But once we go, because of the way the code works, they're facing opposite ways in order to calculate the forces. And now we can do something interesting, which is we could actually give an initial velocity to both of them. And we'll see that they're both initially moving in the x direction, and they have this spring motion. And so we actually get these things sort of added together for free. They both had an initial velocity, and then they're getting a force from the spring, and they oscillate while moving. And if we give them different velocities, so for example, we could have this one set its Vx to be 0 and set its Vy to be 1. Now we can get things like having them be spinning around each other while oscillating. And this all just emerges from having coded Newton's laws into this model. We can now get all sorts of different types of motion, and it's all just coming out of Newton's laws. So that's pretty cool. And we're almost ready to do a molecular dynamics simulation. There's one thing that we want to change, which is right now we're doing the simplest form of numerical integration, known as Euler's method, where we take the current position or the current velocity and then just add the velocity times the time step. This works okay, but there's a slightly more complicated version we want to use, which can guarantee that that in our simulation energy stays constant. So I'm going to show that in the next video, and then we'll go ahead and do a molecular dynamics simulation.